Greetings, traveler! I'm the Calculus Cleric, and today we'll be going over infinite series. So the specific question is to find the interval of convergence of the infinite sums starting at 12 of e to the n multiplied by x minus 2 to the nth power. So there are two ways that I can tackle this. Either I can tackle this with the ratio test or the root test. As we've been doing a lot of ratio tests in the past videos, I figure it would be good to do the root test. Also, they conveniently gave us two nth power exponents, so that'll make it a lot easier to do the root test. So the root test is as thus. And our an value, of course, is just what's inside the sigma. And so substitution. And now we can simplify that by factoring out an nth power from the interior a of n. Okay, and this can also be rewritten as yes, because when you turn this root into exponent itself, it'll be 1 over n, and those two n's will cancel out, giving us 1, and that is what we are left with. Plugging in n approaches infinity will just leave us with this. Now, the root test tells us, similar to the ratio test, that when the interior value is less than 1, then the sum will converge. So therefore, we have to set this less than 1 to figure out what x would be equal to so that this entire series does converge. And so this is our almost final interval of convergence. So now we have to test whether x does converge at these endpoints specified here. So we just test that by plugging in this value into x for the sigma sum above. Okay, so this will cancel out and equal 0. And this is equal to, and that is equal to e n multiplied by 1 over e to the n. So we can factor out an n to get them inside. How convenient, that's a 1. Okay, so that is our final sum when it's simplified out. And basically, we can tell whether this diverges or converges by taking a look at this as, okay, let's do it this way first. So this we can call an infinite geometric series, as the format of an infinite geometric series is that it starts somewhere c of r to the n. In this case, our c, we can call it 1, and our r value, we can also call that 1. Okay, so what does this infinite geometric series tell us? Okay, so basically it tells us when r, the absolute value of r, is greater than or equal to 1, the series diverges. So, if we look at this r value right here, is that greater or equal to 1? Why, yes, it is equal to 1. So therefore, this whole series diverges. by infinite geometric series. Okay, so x is not equal to 1 over e plus 2. Okay, time to test our second point. Negative 1 over e plus 2. Do the same thing, plug it back into the sigma. Once again, we can factor out that n which leaves us with that as our result. So when I take the absolute value of this, we know it will diverge because we figured out earlier before that the sum of, when it's just 1, it'll diverge. And basically, when we take the absolute value, the negative sign will disappear. So now if we take the absolute value of that, it'll diverge. So now we have to test whether it's conditionally converging by just taking, let's see, why don't we try the divergence test on this one? So basically, I set the limit to infinity. And so basically, they want me to figure out whether this converges to 0 or not. If it converges to 0, then the divergent test is inconclusive. However, if this converges to not 0, then it does diverge. And so when we take a look at this, okay, whatever that is not 0. It'll alternate between the two and never reach 0 ever. So therefore, we can say that this diverges by the divergence test. So we know that it's also not negative 1 over e plus 2. So our interval of convergence is just that.